Hello, so welcome back. Today we will be talking about our next research project, our next research topic. So this one is called. Let me just zoom out. Yeah, this one is called hyperoperations in Maslow dequantization. So Maslow dequantization. Let me write it down. Maslow dequantization is one of three ways to go from your real ring R with plus and multiplication into your tropical ring. Tropical semi-ring with T and Maxon addition. Okay, so Maslow dequantization is one way to go between this region to this region, and basically whatever problems you have in algebraic geometry over here, you sort of lose information and you turn it into a simplified problem over here. Simplified problem. So the concept of Maslow dequantization is what we have of interest over here. So Maslow dequantization. So Maslow dequantization is basically a limiting process. And it is defined as such. So if you have two real numbers A and B, then first we define, take this function f is equal to log of fm subscript over here to denote the base. So f base m log of m e to the a plus e to the b. Okay, or rather than e, it was supposed to be m, so I'll rewrite that. So log m to the a plus m to the b. So this is basically our new operation. So this is our operation between a and b. Okay, this notation is a little bit bad, but this is how we're denoting this operation. And the idea of Maslow dequantization is basically, if I take the limit of t tends to 0 of t into a operation m, a by t operation m, and b by t operation, we should eventually tend to the maximum of a and b. So this is the idea of Maslow dequantization. So in other words, if you take the limit of t tends to 0 as t into log base m, m to the power of a by t plus m to the power of b by t, this tends to max of a comma b. This is the idea. Okay, now what we want to generalize is using the idea of a friend on YouTube. I will try to link his channel. It'll be easier, I think. Yeah, so the idea is, instead of having an operation defined as a, b like this, we want to generalize it. So this is where a bunch of other ideas come in from. Namely, the ideas are coming from commutative hyperoperations. Now, what are commutative hyperoperations? Basically, when we had when we're going up our ladder of operations. We have A plus B. This is commutative. We have A into B. This is also commutative. We have A to the power of B, and this is suddenly non-commutative, right? And how did we go from here to here? We said, okay, multiplication is repeated addition. Repeat addition is equal to multiplication. And we just kept doing this iteratively. Repeated multiplication is equal to exponentiation. Repeated exponentiation is equal to tetration. So A by B, like this is how it's denoted, or double arrow like this, and so on, right? And so after addition and multiplication, everything from here on out is non-commutative. And what I mean by non-commutative is that for A plus B, we can always say B is it's the same as B plus A. A into B is equal to B into A. But we cannot say A to the power of B is equal to B to the power of A, right? So this is the idea. We don't want to generalize it in this manner by using this whole repeating drama. Okay, it would be a little bit insulting to call it drama. Let's just leave it. Let's not call it anything. So the alternative thing, the alternative approach is to keep commutativity. So we want an operation that generalizes so that the first operation as this is equal to just addition, this is equal to just multiplication, and this is equal to something new that is not equal to exponentiation, right? So this is the idea behind commutative hyperoperations. And so what we do is that we define our first operation as such. A and B, for A and B are real, is defined as exponentiation of log A plus log B. Okay, this is how it's defined. So if we just simplify this, we know our log rules. So e to the power of log of something, let's say x is equal to x, right? We know this. So similarly, using this, I'm just going to put this in brackets like that. And yeah, and we also know log of A plus log of B is equal to, why did I put a thing there, is equal to log AB, right? So using that, we just say that e to the log of A, log A plus log B is now equal to log AB, and this is all equal to AB. Okay. This is how we define the operation. And yeah, so it's sort of built iteratively, where to go to the next one, this is 1, right? This is 1. So we say we start with our basic operation as this is equal to plus. We start with this assumption. And then we define that A to the power of 1, which is multiplication, is equal to e to the log of A into 0 over here, operation 0, log B. This is how it's defined. And then so iteratively we could say that for I plus 1, B, it's equal to e to the power of log A, operation of I, log B. Okay. Now similarly, what this ends up doing, so what this ends up showing is that we can now generalize the following. So we know that A0 of B is equal to a plus b. This is our assumption. On top of that, we built that a1b is equal to a into b. And now we're going to construct a2b. So this ends up being e to the log of a plus log of b. And for n times, you can see that because of the fact that we have a plus over here, this part remains commutative, right? So if we switch a over here and with b over here, we get the same thing. And this does not contribute anything to the commutativity. So this overall remains commutative. And so similarly for n, what we do is we take x n times, so x n times the whole into log n times of a plus log of b, and this is also n times. Okay, and this is how we define the nth one. And so we can construct this iteratively as well. I plus 1b is equal to e to the power of log of a, the whole previous operation I, log of b. Let me try to explain with an example. So we have this, right? So now I'm going to explain I'm going to explain 2 with respect to this. So this would be e to the log of a into 1, right? Log of b. And so we'll expand this. This is equal to we know iska expansion, right? So this was what? This thing over here. Let me scroll up. Yeah. So we know that a operation 1 of b is equal to e log a plus log b, and we're going to substitute that now. Instead of a and b, now we have log of a and log of b. Log a, log b. So we get e to the power of log of a plus log of log of a plus log of b. Okay, so that's your result proved. And the usefulness of this happens when you consider the inverse case. So for now, we keep going with, right now, all we've been discussing is going like, from 1 to operation 2 to operation 3, and so on for all positive integers, n greater than 0 and n belong to natural numbers, right? Or we can just keep natural numbers. So we need to start considering what happens when we go backwards. So the questions we need to ask is, okay, if I start from the first operation, what is the 0th operation? What is the -1th operation? And so on. So this is the question we found useful to ask. And so the interesting thing is that this is just the exact opposite. So for a general a operation nb, what did we describe it as? X of exp n times. I'm going to put n over here to denote that we're doing the exponentiation n times. And log n, same thing over here for log. I'm going to just write it down in a bit, but this is what we were talking about, right? Log nb. And now I'll just write for clarity, exp of n is not equal to the power of n. It's not exp to the power of n. It's just exp like this. N times. And similarly, log of n in this case just simply denotes log of log of log n times log of something. Okay, so this is what I need to clarify, and that's it, right? This is how we add for n is a positive integer. Now for the negative integer case, we do the exact opposite. So we write log of, okay, so for n less than 0, and now we can generalize it for like all this thing, for all integers. So for n is less than 0, we now say instead that a operation of minus n of b is equal to log n times of exp n times a plus exp n times b. Okay, so this is how we explain negative commutative hyperoperations. So these are negative commutative hyperoperations. Okay, and now if you'll notice, if I put n is equal to 1, I basically get my Maslov dequantization formula. So a over here of minus 1b is equal to log of exp of a plus exp of b. And we know our Maslov dequantization, what was it saying? It was saying the limit as t tends to 0 of t into, now we're going to use our new notation, our proper notation. So a by t operated by minus 1, b by t tends to the max of a comma t. Okay, this is Maslov dequantization. And so what we are wondering in our project is that if we replace this operation here, can we generalize Maslov dequantization? So this would be our project, and yeah, we're going to instead try to generalize. Now we are not sure exactly what role t over here plays, because I'm not exactly sure if, like, just saying into t a by t of minus n, for this matter, b by t, I don't know if this is going to give me a valid limit all the time. I don't know if it's always going to converge to a function. So the role of t over here is sort of, it needs to be treated with caution, because if we're not too careful, the issue is that if we're not too careful, then we will always get max of a comma b. We will always get the maximum of a comma b. We don't get anything else if we just blindly apply this. So for us to actually get, if we are doing it naively, so for us to actually get some new new methods of dequantization. We need to be a little more creative, I guess, about this. And basically, the whole play is about switching our operator over here. So that's the idea right now. Yeah. And thanks to, I forget his name, Joharicus, I think. We got in touch about these hyperoperations, and thanks to him, I am now aware of a formula that looks like this. MNB is given by. Okay, so I'm gonna first define a term here. Okay, so Q to the power of M, and over here Q is equal to the super log. Not Q to the power of M, Q tetrated to M. So Q tetrated to M. Yeah, I'm just gonna write it smaller so that's clear. Q is equal to the super log of M. Now the issue is when he says super log over here, I'm not sure if it's the same as the repeated log, like if log M is equal to log M times. That's unclear to me, but we should check that out. So slog of M into, over here we'll put K1 M tetrated to K1 plus M tetrated to K2 plus X minus 1. The whole like that, yeah. And now I'm going to define the other terms as well. K2, K1 and K2. K1 is given by, again, slog of M super log, okay, slog A minus X minus 1. See, and slog M of B minus X minus 1. Okay, this is how we define our general commutative hyperoperation. Now, yes. So the idea is that instead of taking for a general M, we take it for let M equal E, just for cleanliness, I guess, because we would like natural log instead of just a log of M for now. So that's the idea right now. And so what Jargus has come up with is parallel hyperoperations. Okay, and so our research is basically going to be putting these parallel operations, so it's denoted like this. E to the n. Okay, this is our operation, and we want to find out what happens when we take the limit of t goes to 0 for the hyperoperator for a by t, and parallel hyperoperation of -1 again, e b by t. So this is our current objective. The other research that we can do is almost entirely going to have to do with replacing other operations over here and seeing what we get. And so we expect to lose some information while we undergo this whole limiting thing. And we expect to come change our operations from just a regular addition and multiplication into something different, and we need to study that. So thank you all of you for your time, and that's my summary for hyperoperations and mass law of dequantization.